This is the 52nd IoT Internet of Things New York meetup. Tonight's theme is signal processing and predictive analytics with IoT. So many people not in this room might think of IoT as just that consumer thing, that Nest thermostat. But in fact, IoT is probably a new word for a very old thing that has been around decades. It's that we're connecting a lot of devices. And particularly now, I think both of these might talk about things less consumer, but are going to be ways that we make sense of our machines and devices in our larger world. We also like to thank, we actually have a new event sponsor, NEA, New Enterprise Associates. Lastly, we'd also like to thank Grand Central Tech and Build. Tonight, like I said, we have two speakers that we want to thank. Reality AI, which I hear basically builds tools to help R&D developers develop AI techniques to make sense of sensors and devices. And Augury, they'll perhaps describe it with better tagline, but they understand, they listen intently to machines and hopefully tell you what the, when the machines have a sore belt or something. I wanted to end this by a couple IoT community announcements, which we like to do at the beginning of each meetup. I'm going to take precedence by giving one of our own announcements. A couple months ago, we were lucky to announce latest funding, $16 million round led by Benchmark and NEA. As such, we are rapidly growing, hiring across all areas of engineer, customer success, sales, partnerships, content and event marketing. So if you or anybody you know that might be interested, please reach out on careers.timescale.com. We'd also like to thank DataCamp, which you could find a link right there. And basically, DataCamp provides a lot of interactive courses, online course materials around Python for data science. And they actually allow a free month of, as kind of a partnership to various meetups, they give a month of free access to all of their content for meetup participants. And finally, we should have we're planning the next meetup right now. But if you would like to present or possibly sponsor a future meetup, please let us know. It, of course, has to be IoT related. And we would generally like something that is also of some technical nature and not just a vendor sales pitch. And also, if you would like to host us in your event space, if you have a good space for that, please let us know. Finally, we'd like to kind of open it up if any member of the meetup has any announcements or asks.
Hi, I'm David Gordon. I run a startup called 2 Cents. 2 Cents is AI for devices that learns to recognize you so you never have to enter a password. So I look at the way you behave and build a signature for your specific behavior so that when it's time to authenticate, you don't have to do the work. We have a couple big customers, and we're also a growing team, and we're looking for AI and machine learning engineers. So if anybody's looking, please come talk to me.
Hi, my name is Riddhi. I've just recently moved from Lisbon, Portugal. I had my own startup to do with predictive maintenance of corrosion in factories. And I'm looking to connect to people who are working in smart manufacturing as well as anything related to corrosion. All right, thank you.
So hi everybody, we're a blockchain group in New York City, and we're going to be hosting an AI event in May. And if you have, you want to be a speaker and you work for a company in AI, talk to me because it's going to be a really big space, big event. So, and we're looking for speakers right now. So we're blockchainYC.org.
Stuart Feffer is the co-founder and CEO of Reality AI, a New York City company.
All right, everybody hear me?
Yes.
Excellent. Okay, so I'm Stuart Feffer. I'm from Reality AI, and we're going to talk about what to do when you are trying to work with signal inputs, with machine learning, and building a smart device. Our company we sometimes describe it as an AI signal processing engineer. Our customers are typically the R&D departments of large companies that are building devices instrumented with sensors, are primarily in the automotive and industrial space, but we do also have some consumer products customers. So these are tools that a working engineer can use to expose algorithms to data collected from a collection rig, generate classifiers, detectors, regression predictors, and the like, and then embed that code in firmware in their device at the edge. So, you know, some of the print on here is a little small, but this graph here is showing the unit price of sensors over the last few years and the increasing volume of shipments of sensors. We are seeing right now a virtuous circle where unit prices of sensors and microcontrollers both are coming down fast. That's driving increasing utilization, and more companies are putting sensors on their devices and trying to do something with it. The average non-autonomous car today has 200 sensors and 30 microcontrollers on it. A luxury vehicle, maybe another 100 sensors on top of that. We're finding smart devices from vacuum cleaners to toothbrushes, all across the continuum. Now, the problem is that particularly when you're dealing with signal inputs, it's hard. What many of our customers have found is that when they move from an environment where they are using, say, in a predictive maintenance kind of application, where they're moving from an environment where they have a smart engineer using expensive test equipment and looking at one particular machine, and now moving to a world in which there's ubiquitous sensors on every machine, monitoring them continuously and trying to automate that monitoring, they're seeing a lot more variation than the engineering models can accommodate. If you also need to do your real-time prediction at the edge, then your options are even fewer, particularly if you want to use machine learning. Deep learning has been a real boon in many fields, but it requires a lot of hardware when deployed at the edge. And that drives pricing. So if you need to do something in a device, do it locally, and meet a price point, your options are few. And that's really where we come in. Now, today's theme is sensor data, signal processing and AI. So the first thing I want to talk about is what is the difference between sensor data and signal data. We talk about the difference between things that change fast and things that change slow. Event logs, periodic sensor readings, these fall into the realm of sort of time series analysis. There are a lot of good tools for working with that. But when you are dealing with an input with a very high sample rate, sound, accelerometry, vibration, electrical signals, and the like, you're in the realm of the signal processing engineer. These are physical waveforms. They have properties that points of time series don't necessarily have. Jitter, phase shift, transients, and so on. Sound is a lot more than a time series of pressure readings. It's a physical wave. And if you don't accommodate that in your analysis, you're not going to be able to make sense of it. The other challenge in working with signal data is the dimensionality. If you're using a vibration sensor on a piece of equipment, sampling it at 1 kilohertz, and it's a 9-axis accelerometer, that's 9,000 data points per second, floating point, that need to be analyzed, transferred. It'll blow up a lot of machine learning algorithms. So you need different kinds of techniques. So where do you see these kinds of applications? Well, automotive, consumer products, condition monitoring and predictive maintenance in industrial settings, as well as in the automotive setting. And you see a wide variety of sensors, sometimes which you want to be able to combine in a sensor fusion environment to be able to maximize your chances of identifying the condition or the event you're trying to detect. All right. I'm going to show a quick video that just shows our product and some of the things we do using a simple example from a fan, just so you can kind of see what we're talking about here.
Hi, I'm Stuart Feffer, co-founder and CEO of Reality AI, and today I'm going to give you a quick demonstration of the kind of thing you can do using our technology along with an accelerometer or vibration sensor. And today for our sensor, we are using the Bosch XDK, and we're using the accelerometer on this box to, at the moment, identify what I'm doing while I move around. As you can see on the screen over here, at the moment we're using it as if it's part of a wearable. And as I move my arms, it's identifying what I'm doing. If I'm moving my arms around a lot like this, it figures I'm presenting. If I stand here quietly, it will decide that I'm standing. And if I start walking around, we'll switch to walking. We even put in a jumping jacks detector. Okay. Now, that's certainly one use case for Reality AI, using accelerometry for human activity identification. And we are working with a number of customers to do that right now. The other way we're using our tools is on machines for predictive maintenance and machine health. So I'm going to take the same sensor and I'm just going to put it right here next to our stand-in for a piece of rotating equipment, a small fan. When I turn on the fan, it's going to shift to off speed, and when the fan is fully up to speed, it'll just say that it's attached to a blower that's on. Now, I can also block the input. And it's going to detect that the input is blocked. Finally, if I turn off the fan and I insert this small piece of cardboard and I create a little imbalance condition inside the fan, once again it'll say that it's off speed and then detect that it's unbalanced. So what you've seen here is we've detected, number one, what kind of thing am I attached to? A human being, something stable, or something vibrating like a fan. Where on the efficiency curve for that fan are we at this particular moment? And we're also detecting dynamic load changes like an imbalance. Okay, now let me show you how you actually create a classifier to do this using our tools.
Here's the software you'll use when you work with Reality AI. Like any machine learning application, it learns by example. So for the purposes of this demo, we recorded the fan operating for about 2 minutes in each of the several conditions that we wanted to be able to detect. Here's an example of vibrations recorded when the fan was operating normally. And here are some examples of vibrations recorded when the fan was operating with the input blocked. Once your data is loaded, it's as easy as picking a base tool configured with our help, selecting the data you want to train against, and hitting the train button. You'll also get a complete set of validation statistics, tools for helping you continually improve your classifier, and options for deploying either to the cloud or to your embedded target. Thank you. We look forward to working with you.
Okay. So just a couple of examples of the kind of thing I'm talking about. One of our customers is a firm called Man & Hummel. If you've never heard of them, they are the biggest maker of filters and filtration systems in the world. Air, fuel, water, that kind of thing. And they have a new product out called Sense-It, which is intended to monitor the load on an air filter on a piece of agricultural equipment, construction equipment, or fleet trucking. So this device over here gets plugged into the servicing port on the air filter assembly, and it will predict the remaining useful life on that filter and transmit that to a application that the fleet manager can use. They could look at it on their iPhone, iPad, PC, or what have you. Now, Man & Hummel is a company that knows more about filters and filter engineering than anybody else around. And what they found was that when they started putting this into production, well, there are a lot of factors that are going to affect the readings that they get on the differential pressure across that filter, which is the basis for the sensing. It depends on where the throttle is set on that vehicle. Is it going uphill or downhill? What's the humidity at that particular place and that particular time? All of these factors can affect the readings, and they can't measure all of those inputs to their engineering model. So they turned to machine learning. And they're working with us now to develop a suite of better predictive models for the remaining useful life on their air filters. And we'll probably be adding some additional sensors in the next iteration of that hardware. Another customer of ours is a firm called Coito. Again, a name you may not have heard, but they make a significant percentage of the headlights on the road today. They're a primary supplier to Toyota, Ford, a number of the other OEMs. And they have a new product which they just announced at the last CES, featuring Reality AI technology for something called adaptive driving beam headlights. So this is a headlight that is it's a smart headlight. Your high beams are on all the time at night, and it will use a camera to detect when there's a car in front of you, either oncoming or going away, and selectively cut out just the part of the high beam that would blind that driver. They use an array of LEDs to selectively turn on and off part of the beam, and expect at some point to move to scanning technology. This is actually on the road today in Japan in an early version, and I believe also in Europe on high-end vehicles. But the current versions, I am told, are prone to false positives. If there's a bright vending machine or a storefront, you might think that's a car or a truck and cut out the beam. So they've also turned to machine learning to try and generate a better model that can better detect those vehicles and suppress the false positives. Now, if you've been to any AI conference, you know that drawing boxes around cars is a solved problem. Right? There are any number of demonstrations of people tracking vehicles across the screen. The trick here is not to find the vehicle. The trick here is to find the vehicle in a manner where you can run it on a processing unit that fits the price point of a headlight. Right? This isn't an autonomous vehicle driving stack. We don't get to tote a server around in the trunk to do the job. It's got to be a cheap microcontroller. Okay? So that's the kind of problems that we're talking about here. Now, if you are working on a device with a signal processing kind of input, and you're trying to figure out how to proceed, I have 3 big tips for you. Number 1, use rich data, not poor data. Number 2, it's really all about the features. And number 3, there will be compromises and trade-offs. Nothing is perfect. So let me go through these in some more detail. First, I want to talk about rich data, poor data. Now, we tell our customers, when you are thinking about your instrumentation and your rig, collect as much of the time of that raw time series signal as you possibly can. Don't discard it. Don't use it. Don't compute averages or even an FFT. Keep as much of it as possible. So what you're looking at here, I know it's a little faint, but this is actually from a customer who in their first attempt to do predictive maintenance in their factory, they had used accelerometers and only kept basically mean energy in the acceleration at any given point in time. So what you have here is X, Y, and Z, and it's a big squiggly thing, but each of these points in time, they're like you get one sample every couple of minutes. This time series is absolutely useless for predictive maintenance. I mean, really the only thing you can do from this is tell which direction gravity is. Right? Now, a much better approach would be a FFT, fast Fourier transform. How many of you are engineers? I think I saw a bunch of hands when you were asking. So you know what I mean when I say an FFT. FFT is every engineer's go-to for a signal processing problem, because it's what you learned in engineering school, right? I mean, every tool supports it. It's the thing to do. So, but what you're looking at here is, again, X, Y, and Z are the different colors, and we've taken every one of these points, and it's now been exploded into the frequency spectrum of vibration during that interval, the same interval for which that average was taken. You run a Fourier transform on it and get the how much energy now is in each frequency band. This is a lot better. We can do something with this. This can tell you something useful, but it still discards all of the information from the time domain and some of the information from the frequency domain as well, because These bands are picked, again, probably for reasons of convenience. Now, the FFT became popular and widely used because it is much easier for a human analyst to interpret this than the raw vibration time series, which looks like that. This is the raw vibration from which that FFT and those averages in the first slide were computed. Now, human beings can't do much with this, but machine learning algorithms can. So if you are, that's my first tip. Use rich data. Keep as much of it as possible. Don't discard the time domain. Don't discard any bit of the frequency domain. Keep as much of it as you possibly can. I love this example. This is from an Autodesk blog, but it really shows why you don't want to use aggregate statistics. And every single one of these images has the same x mean, y mean, x and y standard deviations, and xy correlation. If all you're keeping is aggregate statistics, what patterns are you missing? Okay. All right, so rich data, poor data. Now, the second point I'm going to make is it's all about the features. Because
T-Rex is the best.
anyone who's worked in AI will tell you, if you have good features, most any algorithm will find what you're looking for. When I talk about features, I'm talking about what are the specific parameters, the specific input variables you put into that machine learning algorithm. Now, at Reality AI, what we're really all about is feature engineering. We spend 80-90% of our R&D dollars and 80 to 90% of our processing cycles on discovering optimized features. This is just a screenshot from our application, but basically what it shows is you pick a sample list and it will run through about 200 or 300 families of features and try and discover from that data an optimized feature set that maximizes the separation between the training classes. We'll do everything from a variety of takes on the FFT right on up through compressive sensing, sparse coding. We throw the mathematical kitchen sink at it if we need to. And at the end of the day, what the thing will come back with is, okay, here are our two candidates for best. How complex are those feature sets to actually compute? What are their relative accuracies? And now the design engineer can make a trade-off. Am I willing to trade a couple of points of predicted accuracy for if I have to use a slightly more expensive chip, for example? Okay, so yeah, it's an automated semi-supervised process. Yeah, okay, I'll go through that. Now, like I said, you could think of this, instead of using the FFT, we are dynamically discovering from the data effectively a custom transform for this particular problem. And the issue with the FFT, like I said, it's a tool of convenience. People use it because they know it, and the tools support it. It's a bit like the old joke about the drunk who drops his keys in a dark alley, but looks for them under the lamppost because that's where the light is better. What I have here are two spectrograms for the same signal input. One showing the results of an FFT. So what you've got here, the vertical axis is frequency, the horizontal axis is time. Brighter colors represent more energy in that particular frequency band. And then on the other side, we have the features discovered by our algorithms projected back down into that time frequency plane. And you don't really have to be a signal processing engineer to see that this thing on the left is a lot less blurry. You've got a lot more definition on the signal. And we've got a couple of low continuous hums, a series of escalating chirps, and some other stuff going on in there. Okay? Okay, so if you're using these features rather than these features, your machine learning problem just got a whole lot easier. And that's our primary way of addressing the embeddability challenge. Do the work to get the best possible features right up front, and then you can use the lightest machine learning algorithm. it's a classification, we can pick it, in fact, for on the basis of what output the customer needs. If it's a classification problem, we use an SVM. That's usually the most computationally efficient classification algorithm, that type of thing. So we can deliver something in a very, very compact computational package. Okay, so number one, use rich data. Number two, focus on the features. Number three, compromises and trade-offs. Nothing is perfect. There are going to be trade-offs, particularly in embedded projects. The sampling rate, the detection window together pretty much determine how much memory you're going to use. The longer the detection window, the higher the sampling rate, the more powerful chip you're going to need. It's worth taking the time to downsample, retrain, and see how you do. Try shorter detection windows, see how you do. That's the best way to optimize. You can build a curve for sample rate by detection accuracy, and usually it'll kind of hover along and then fall off a cliff. So when you can find that sweet spot, you can make exactly the right trade-off, optimize your cost, weight, processing power on the device. Okay, and that is my presentation.
Questions? Hold it up.
Sure. Hi, thanks. This was really interesting. I'm wondering if you guys address some of the fusion issues if you have multimodal sensing, especially with heterogeneous sensors that give you very different types. Have you looked at if you guys are going to be going with a late fusion model or early fusion and evaluate how those two perform against each other?
Yeah, so essentially what we do is we just line up the data channels, and as long as we can get some kind of time correspondence between the different sensors, our stuff will still work. This stuff was originally built for military and intelligence kinds of purposes, and back before this was a commercial thing. I know my co-founder used this for the Air Force Supercomputer Center, with many thousands of data channels and different types of sensors. So the main thing for us is really that there be some kind of time correspondence. If we can't get the timing to line up between the sensors in some way, then it's hopeless. Yeah.
I got it here. Got a mic for him. Hi. I got it here a little bit late. I missed this part. Just a very simple question. I'm wondering, your algorithm mainly running on the edge or on the cloud?
Yeah, so we support both. When our stuff is done, you can either take that finished classifier or predictor and hang it in the cloud and hit it with an API, or you can push it out in a form suitable for embedded use in firmware. So we do support both. I would tell you that probably 75% of our customers are headed for embedded use, just because there are a lot of cloud solutions. If you can throw server-grade hardware at it, they're probably you don't have to work quite as hard to optimize. So most of our customers are doing embedded stuff, but we do support both. In fact, this is probably a good point. Even for our customers who are doing embedded projects, what we tell them to do is test it in the cloud first. Build a prototype device, use a cloud API, field test the heck out of that AI piece, because doing the embedded integration is going to introduce a whole nother group of problems. And when you're debugging those problems, it's best to know that you have confidence in the detection ability of the classifier, and that's not the problem. When you know what results to expect. Even for embedded use, even for an embedded project, there's still really good use for cloud-based.
So my understanding from the presentation is that you do
as much of the work up front as possible for your feature engineering.
Yeah.
Doesn't the chip still have to do that if it's taking in the raw data from the world?
Well, it still has to do the computation, but it doesn't have to do the discovery. So I guess the comparison I would make is to the way deep learning works versus the way we work, right? So deep learning, as I'm sure many of you know, is sort of based on this analogy to the visual cortex. There's many layers of neural networks, the lowest layers of which I think you can fairly describe as basically doing the feature discovery. They are figuring out what features matter to those top layers of that deep learning hierarchy. What we are doing is instead computing features in the form of a transform, right? So we'll represent those features algebraically in a form that is it's going to be more computationally efficient than many layers of neural networks, because deep learning typically needs to bring all or most of that neural network machinery with it into the field. So what comes out of here is this algebraic expression, which, you're right, must be evaluated by the chip in the field, but you can calculate, an electrical engineer can look at it and tell you how many operations it's going to take to evaluate that expression and how much memory it's going to require. So
you can't learn in the field, those are hard-coded.
Well, now it is possible for us to have built this in a way that we could learn in the field. And in fact, in some cases, we will build something where we'll learn particular configuration parameters dynamically in the field. But what most of our customers tell us for these kinds of applications, industrial, automotive, when we describe for them that, okay, look, you're talking about learning in the field, but what that means is your product is not going to behave at your customer site the way it behaved in your test lab. And you're not going to be able to predict ahead of time exactly what it's going to do. Well, they break out in hives. So for the kinds of applications our customers are typically working on, the headlights on the vehicle, that type of thing, they actually don't want dynamic learning, they want controlled learning. So if they can collect additional data, retrain, flash the configuration parameters back down to their devices, maybe through an over-the-air update or something else, and so give the devices the benefit of additional learning, but only after it has been controlled and tested by the design engineers and the quality control engineers.
This guy I'll take up the, let's have these last two.
Thank you. So this is kind of like a follow-up to what you're saying. So OTA updates are very interesting. How often typically people do OTA updates? And then as a corollary, data, as you're saying, data in the field is usually more interesting than data in the lab.
Yeah.
But there's also constraints. So do you typically get data back from the field, or what do you do there? And what are the data approaches to kind of collect that? Are you using 3, 4G, or are you kind of waiting until people come back, or down, whatever? I'm just kind of curious there.
Yeah. So what most of our customers will do is they push their product, which is not necessarily collecting data and transmitting it back, but they will also deploy a version of a rig that is capable of collecting and transmitting, that's running the same classifiers, so that they can pull it in and do more with it. We are actually working right now with Siemens on a rig that we can make available to our customers to do exactly that, using LTE and for transmitting data, primarily focused on vibration and sound. I'm hoping we're going to have that available before too long, maybe a couple more months. But in terms of the frequency, quarterly, semi-annual, annual, most of these guys don't want to do it all that often, and their design and their testing and certification processes take some time anyway, so they typically aren't doing it like very rapidly.
What's the sample rate in that case?
Well, sample rates really depend on the problem at hand. I mean, we've got one customer making a smart vacuum where 50 to 100 hertz is fine, but another company that's doing pumps for mining where you need kilohertz, 2, 3, 4 kilohertz range.
And Saar Yoskovitz is also the co-founder and CEO of Augury, which is both based here in New York and in Tel Aviv.
So hi everyone. First of all, I want to start with a correction to Mike earlier. We're not based in Tel Aviv. We're in Haifa, which is like Tel Aviv but better. It's like 40 minutes up north. I saw earlier, I noticed that it's roughly like 50-50 business product people and engineers. So I'll try to cater to both teams here, and I'll try to speak louder. So first of all, a quick introduction to myself. I'm an engineer by training, studied in Israel in the Technion, electrical engineering and physics, worked at Intel for a number of years in the CPU division. Was an analog architect there. And roughly 6.5 years ago, dropped everything together with my co-founder and started working on Augury full-time. Relocated here to New York 3 years ago to open the customer-facing office. Today we are 80 people. 50 of us are in Israel, where we have the product engineering teams, and 30 of us are here in New York, where we have the sales, marketing, customer success, and biz dev. And our goal at Augury is to help answer this question, right? What would happen if you could predict mechanical failures before they actually happen? And actually, before I dive into this, one interesting thing to notice in this presentation is that we're kind of similar to what Stuart was talking about, but we chose a very different way of approach to the market. Whereas Stuart is more of a horizontal platform, we're more vertical, right? We chose one problem to solve, and the whole product is different, and I think there's room for both types of companies. So our goal at Augury is, to answer that question, as I said earlier. And the facility management or maintenance market has been on this path over the past century, right? Starting from reactive maintenance, where you basically wait until the machine blows up and then fix it or replace it, through preventive maintenance, which is what we do in our cars. Every year, every 10,000 miles, you replace the oil, the belts, the bearings, everything you can, just because someone told you to do that. And somewhere in the 90s, we saw glimpses of predictive maintenance towards the late 80s. And the idea of predictive maintenance is, instead of replacing everything every year, do it when it matters. Do it based on the condition of the machine. And until very recently, it's been a very manual process. So it required expert engineers going out to the field, taking recordings, analyzing the data, and knowing what the health of the machine is. And lately, in the past 5 years, decade, through the introductions of connected sensors and this AI or machine learning analytics platform on top of it, we can do better than that, right? We can take the manual labor out of the picture and help facilities move from focusing on machine health to focusing on business outcomes, right? And this is where we play. And our goal is to help these facilities, switch from the old way of doing things, which is a lot of firefighting, to the Augury way, right? Put some sensors on a machine, connect it to the internet, and you have full transparency to the health of your facility. In a sense, we're building this nervous system that sits on top of all these connected machines. And our goal here is to give the right insight to the right person at the right time. If it's a technician, it's a technician. If it's the bearing supplier, why don't you ship the bearing beforehand, right? If it's a facility operator or manager, let him know as well. We focus on 3 main types of machines, more on the infrastructure, rotating equipment in facilities. Could be commercial, could be industrial. We also do process machinery in certain segments. And we're very agnostic to what this machine does, right? So a pump, as an example here, could be pumping cold water in an office building for cooling, or a hospital, or it could be pumping chemicals in a pharmaceutical manufacturing line, or this is a steel manufacturing facility, right? Today we have 2 products. Just give me a second. The first is a portable diagnostic tool where we basically connect a vibration ultrasonic sensor to a technician's iPhone or Android device, right? And they just walk up to the machine, attach the sensor with the magnet, and within seconds or minutes, they know exactly what they need to do in order to fix that machine. Right, you can pass this along. And then the second product, we can pass this from here. The second product is continuous diagnostics, where we take the same sensors, put them on the machine, connect them to the internet, and now we can provide ongoing alerts if anything changes or goes wrong. And the more customers we get, the more data we get, right? We'll get to it a bit later. There are very different types of data, right? You can see here the white line is portable recordings, and the blue line is continuous recordings. And you can see that there's a number of order of magnitudes difference in the amount of data. But there's also a very different strategical importance to each, and we'll talk about that later on. And before we go to the more technical side, let's talk about predictive maintenance a bit. So we asked this question earlier, and this is a good example. It's a motor that was in charge of refrigeration in a food factory, right? And it started developing cracked rotor bars, which is what you see over here. And once this happens, it starts tearing up the inner windings of the motor. So had they continued to use it for another 5, maybe 6 months, it would have broken down beyond repair. Now, a new motor would have cost them $150,000, whereas fixing it at this stage only cost them $20,000, right? And this is the power of predictive maintenance. The sooner you catch a malfunction, the easier and cheaper it is to actually fix it. And as we work with our customers, our goal is to help them switch from their current state, right, the distribution of machine health, where somewhere between 50 to 60% of machines are in acceptable condition, all the rest need some kind of repair, and gradually over time get them to the holy grail where 90% are in an okay condition, and they can really control the maintenance and the cadence that they want. And as I said earlier, predictive maintenance has been done for over 30 years now. So it's been already proven to be really efficient in cutting down maintenance costs by 30%, eliminating almost all of the breakdowns, and even reducing energy consumption by up to 20%. But the problem is that it's stuck in the very high-end markets, right? So today, only 12% of commercial facilities do predictive maintenance. And we want to help the other 88% make that switch. Now, the reason that it's so hard today is that the current solutions are these big, rugged tablets. They cost over $20,000 just for the hardware. And if you can see on the screen, they give you the raw vibration data. And the only people that know how to read these graphs and understand what they mean are certified vibration analysts that have years and years of training and experience. And in essence, they're like machine doctors, right? And instead of showing the raw data, we give the user actionable data, right? So we tell you, you need to replace this bearing in the next quarter, so plan for the next downtime event and order spare parts. Right, we also have this philosophy in-house where, if you can use Facebook on your iPhone, you should be able to do predictive maintenance. And when we designed our apps, both the mobile app and the web app, which we'll see in a second, that guided us, right? So we show a lot of pictures. Does the machine look like this or like that, right? Put the sensor over here and press this blue button, right? And then when the results come in, it's in very plain English, right? You have misalignment, you need to do this. For continuous machines, we also show the trend of the machine on the web app and also on the mobile. And then when you dive deeper, we give you possible causes and recommended maintenance practices. So if you're a technician and you don't know what to do with misalignment, we tell you, right? Or what to do with electrical faults, we help guide you through that process. And if you are a vibration analyst, we provide full access to all the raw data, and you can provide you can change the analysis or diagnostics online. And once you do that, it propagates throughout the system, and wherever you access it, you always see the last result. So, our continuous diagnostic system has two components. One is the endpoints, which you're playing with now. The second one is this node, right? The endpoints are battery powered, so power efficiency is really important for us. They communicate with the node via Bluetooth, BLE, low energy, and then the node is powered, so it connects through Wi-Fi or cellular to the cloud. We also do some analysis on that node. And this is a very clean room. It's actually a wastewater facility, so it's not. Inside the machines, it's not that clean, but outside, it's very nice. And in reality, it's messier. So this is a steel manufacturing facility. And as you can see, it's physically dirty, so there's a lot of grease everywhere. There's also a lot of noise, and we collect noise, right? And there's a lot of steel and interference for the sensors. So when you go to market with an industrial solution, you need to make sure that your system is robust enough to work in these environments. We had an installation in a power plant somewhere in the Midwest, and Sean over there was in the installation. He's our account manager. And we learned that, how cold was it? 0 degrees. At 0 degrees, the epoxy freezes. That was news for us. So what do you do then? You have the sensor, everything is connected. You just want to put the sensor on the machine, but the glue doesn't stick, right? So when you work in these environments, you need to make sure that you have a robust solution for every challenge that you'll face, because you'll face all of them. Now each one of these, I'll just run through all of them. So each one of these endpoints includes a number of different types of sensors. We have a triaxial vibration sensor. So every endpoint measures the 3 directions, right? We have a magnetic emission sensor, which we use for electrical fault diagnostics. There is a temperature sensor. We actually have 2 of them, one for the ambient temperature and one for the bearing temperature or the skin temperature of the motor. And then we have a low power vibration sensor that is always on and always listening. And if something abruptly changes, we wake up the higher end system and take a full recording there and then. And one of the biggest challenges is, how do you fuse all these sensors, right? How do you correlate between magnetic emission and vibration, or a rise in temperature with the RPM changing, right? And this is a lot of know-how and domain expertise that we've developed in-house by having machine learning engineers sit with mechanical engineers that come from the vibration analysis, come from the mechanical engineering domain. And this is the only way to cross-pollinate, right, the 2 fields. One other thing we do is we have up to 4 endpoints per machine, and we sample all of them synchronously. So we actually have 16 data streams that are synchronized. And we can use that to do more advanced analytics, like phase analysis and other types of analytics, where we have a holistic picture of the whole machine in real time, right? How it's moving in space. Once we get the data from the sensor, we have 3 steps for the diagnostics. The first is anomaly detection, right? So we build a specific model, if you will, for every machine that we are on, right? And we can detect an anomaly. Something has changed, even though we don't really know what it is yet. Now, naively, it's fairly simple, right? But as it happens throughout the day, machines in these industrial and commercial facilities change the operating conditions, right? So you can take 2 recordings of the same machine. They look totally different, but they're both OK. Right? So how do you build this model over time to really detect when something is really different, not just the operating condition changed a little bit? Once we detect something, an anomaly, we go to fault detection, right? And here we compare this machine to all the other similar machines we have around the world. Again, we have this malfunction dictionary that includes 40,000 machines across different segments, different health, different operating conditions. And here we can tell you specifically what's wrong. And then the third step is expert verification. Now, this is really important. What we've learned is that if you need to replace a $1 million chiller, you don't want to get it from an app, right? You want a human being to call you and provide more insights and more information on why that is the case. Our algorithms, on top of giving severity and malfunction type, also give a confidence level. And if the confidence is below a certain threshold, we then send it to our in-house expert vibration analysts, and they verify the results. Or if it's a critical machine in danger, we also run it through them. And we also have an external network of vibration analysts where we send backlog recordings for them, anonymized data for them to analyze. And this is also really important for machine learning. The worst thing you can do is build a machine learning algorithm based on one person, one expert. because every single expert has his own biases, right? And you want to increase the number of voices in the mix. And because we're in a very specific domain, we couldn't use mechanical Turk, right? We can't send hundreds of thousands of recordings to random people and ask them what's wrong with this machine. So we had to build our own mechanical Turk, basically. So we have tens of, close to 100 vibration experts that we randomly send data to, and they give us their result. And another very important feedback loop is the end user themselves, right? Using our app, they can add observations, they can add repairs. So they tell us, I just had to replace this bearing, right? Either we didn't tell them to do it and we learned something, or we told them and then we can see the machine was in danger, they added the repair, now it's in green, good for us, right? And as we go through these iterations, our accuracy goes up. This is an old graph from 2016. We track our accuracy across every different malfunction that we can diagnose, which are in the hundreds. And across the board, we're above 95% accuracy. Right, these are two examples, misalignment in gray and radial unbalance in blue. Right, and you can see how it goes up over time. So now let's go into the more engineering side of things. Stuart gave a really good intro earlier on to spectrum versus time domain. And in the vibration world, it's all about the spectrum, right? Mostly about the spectrum. And when you look at a machine, different malfunctions and different components appear, or malfunctions in different components appear in different places in the frequency domain, right? Now, traditionally, vibration analysis, which again existed for over 30 years, has been a pattern recognition course. So every vibration analyst gets they actually have 3 books this large, and they say, if it looks like this, it's an electrical problem. If it's this, it's imbalance, right? And then a vibration analyst, through this training and decades of experience, knows how to start identifying malfunctions. Now, if you look at the data itself, these are recordings. These are not the multiple recordings of one machine, right? They are recordings of different machines that all share the same malfunction. In this case, it's mechanical looseness, right? And you can see that they're very similar to one another, right? They're all aligned to this, what's called the first order, which is the RPM frequency, and then something appears in 2 times the RPM frequency, 3 times, 4 times. It's very neat, very order-based, very synchronous, as it's called. And if we take all these graphs and put them one on top of the other, it looks nice, right? There, you have a classifier. You don't need to do anything, right? Unfortunately, some malfunctions aren't that easy. Right? This is bearing wear. Again, multiple recordings of bearing wear, one on top of the other, and it looks like random garbage. So going back to feature engineering, which Stuart discussed at length earlier, the question is, how do you select the right features that separate bearing wear from misalignment, right? And by combining domain expertise and trial and error, you can find simple features that really separate these 2 groups, right? So here, this is bearing wear, and these are imbalanced recordings, right? So by running a simple statistical function on the signal, you could separate these 2 malfunctions. Now, obviously, when you go to different configurations of machines, different operating conditions, different environments, it kind of gets a bit messier, right? And this is like the art behind the machine learning science or feature engineering. And as we get more and more data, we open the door to deep learning, right? And I don't know how many of you follow the developments in this world. Somewhere in the past 5 years, we've seen a jump in the accuracy of speech recognition and image recognition, right? And it's mostly due to the changes in technology and algorithms that enabled us to open the door to deep learning. Unfortunately, in our world, there was never enough data to get there, right? So for deep learning, you need hundreds of thousands, millions of samples of recordings. And we're now at a stage where we can start using deep learning in order to both predict anomalies and detect malfunctions. These are two graphs of the blue line is the original spectrum. The red line is a predicted spectrum based on a training that we did based on a number of different machines and recordings, right? So you see that we're getting very close now, right? Where the computer knows how to predict the next step. And this is really where we're going. This is what will provide us the next order of magnitude of accuracy changes. So how does this all play out? This is a case study from a data center. I can't name them, unfortunately, but they're a Fortune 5 company. So you have 5 guesses. And this data center has 1,000 fans and pumps in one facility. Right? This company has tens or a couple dozen of them. And we installed our sensors, continuous diagnostic sensors on 20 of these machines and started recording. And we identified 2 very different things. One is operational and the other is mechanical. Here, the good thing about these machines, you can see them over here, they're arranged in grids of 3 by 5. So every 15 fans have the same controller and therefore follow the same operating conditions. And this is what you see here. They all go up and down. The vertical axis here is the vibration level. This is the time domain. And each graph, each line is a different machine. So you see that they all go up and down, aside from this orange one, which behaves differently, right? And maybe this brown one and purple one up there as well. So if you have data from multiple machines in the same facility, you can start detecting anomaly not only in the machine itself, but compared to other machines in the same facility, right? And another thing to note here is that somewhere in July, something changed, right? We can all see the vibration levels went down. And what happened is that throughout the day, the controller changed the RPM of the fan, right? It's called a VFD, variable frequency drive. It changes the speed that the motor rotates in, or the fan. And when they hit a certain frequency, I think 1400 CPM, RPM, the whole structure started to shake. So it's called resonance frequency, right? So the whole structure started to shake. And the only thing they needed to do is tell the controller, don't go above 1200 RPM. And the moment they did that, vibration levels dropped an order of magnitude, right? Why do we want to lower the vibration levels of machines? Because it increased life, right, of the machines, lower energy. And this change, if they do it across their facility, again, they have 1,000 of these fans, right? It translates into real dollars at the end of the day. Another example from the same facility is a critical mechanical failure that they had. And without even knowing anything about vibration, this graph, what it means, this is the time domain, right? And each row is a vibration reading, right? Without knowing anything about anything, you can see that something changed, right? And after 10 days, it went back to normal, right? That's good. So what happened? They had bearing wear develop in 4 days, from 0 to full blown. Typically, it takes 6 months, right? So we were kind of baffled by this as well, because our team never saw, our vibration experts never encountered this. And what we enable them to do is identify the problem, right? Get spare parts and replace the motor in 10 days before any malfunction happened. Now, it turns out that this motor had a design flaw from the OEM, where they had something that sits on the bearing and kind of ate it until it wore out. And they have 200 other motors of the same model in their facility, right? So now they go to the OEM and they have real data. They have snapshots every 30 minutes, right? this is how the malfunction developed, and they demanded them to replace the whole 200 motors. Right? So this is real power for the facility. And also for the OEM, they never saw this malfunction develop in real time and had all the data to support that. So, we're on this trend of exponential, right? And I said earlier that there are two different types of data. And the sad truth is that if you record a machine for a full year and it's in an acceptable condition the whole year, you can throw away 95% of the data. It's worthless, right? Whereas for the portable tools, every recording is a new machine under a new operating condition in a new facility and probably a different health status, right? So there's really a different strategic value to these types of recordings. And for us, as we look into the future, on one hand, this is good, right? It's good to be exponential. Everybody wants that. On the other hand, it poses a real challenge for us, right? We sample 15 gigabytes of data per machine per month. And if you have 100 machines in a facility, right, and you want to transfer all of that via LTE or cellular, you have a real problem, right? If you want to store all of this in the cloud, you have a real problem. And run algorithms on all of this, you have a real problem. So for us, the next stage is how do we move to edge computing? How do we filter out most of this data in the node, in the room, as close as we can to the sensor itself? And on the flip side of that, what does this data unlock, right? What other possibilities does it unlock for us? Does it unlock for our customers? Sean, don't get a heart attack. This is a comparison that we made for one of our OEM partners, which should be anonymous. Yeah, I did it correctly. Where we show them compared, we see the whole market, right? You develop, you design and manufacture this machine, right? Now, statistically, you're on par, like acceptable monitor alarm danger, you're on par with the rest of the OEMs. But when you dive deeper into malfunction type, all the other OEMs, you're much better than them in this malfunction. But over here, something is off, right? What caused this? I don't know. Let's go into the data and see, show me all the machines that have this malfunction. I want to know where they're at. I want to know what happened. And it enables them to really understand how their machines are being used. If you're a pump OEM today, it kind of depends. But most of them, you sell to the distributor, and you don't know where the machine ends up. I was on stage in one of the maintenance conferences with Grundfos, the largest pump manufacturer in the world. And the head of aftermarket services said that they know where 4% of their machines are. 4%. How are they used? What type of functions do they have? Why are they caused? Right? Does your customer like you? Right? What is the brand loyalty? They have no idea. And this is a way for them to bypass the distributors and build this brand loyalty. And another thing that all this data enables us is to start looking at other types of machines. So we had a hackathon, and we wanted to see what we can do in 2 days. So we start by understanding how it works, then taking it apart because we're all engineers and we like that. We'll see in a second. We try different sensors, where to place them. Initially using lab equipment. And then eventually using, this is the internal part of the endpoint that you saw earlier. An oscilloscope, an endpoint, and we started stimulating different malfunctions. So different things you do in the house, like vacuum a whole pile of dirt. Everybody does it. I won't show the data here, but within 2 days, because we have the full stack from the sensors all the way to the cloud and the research environment, all we needed to change was the algorithms, right? So 90% of the work is already out of the box for us. And within 2 days, we were able to really identify different malfunctions and different operating issues with the machine. Right, so for us, we're starting in the industrial, commercial industrial sector with the goal of eventually diagnosing everything that has moving parts, right? And that's what I said earlier. It's similar to probably to Stuart's goal, but we have a very different approach. And the market is large enough. I mean, there are enough machine types around us for a lot of companies to pursue it, and we see more and more companies take form in the past couple of years to try to solve this problem. So with that, I try to keep some time for questions. And just to make sure you ask the right questions, I brought a list of interesting ones for you. So if you have any other questions, I'd love to discuss them. Yeah.
I find it really interesting how you're aggregating data across all of your pumps.
Mm-hmm.
So first question is, do you have to calibrate for every single pump in each individual location? And then second part is, if you look at it in aggregate, do your clients start becoming sensitive about their data? Because what they're realizing is that they're contributing to an algorithm that gets better, but it also helps their competitors.
Good. Two questions. The first one, the best example I always give is that when you drive your car, in New York people don't have cars, but when you drive your car, you can sometimes hear the fan belt is squeaking, right? And you know that you need to replace it. And it doesn't matter if you're driving a Mercedes or a Toyota, the fan belt always sounds the same, right? So the make and model don't really affect it. The operating conditions don't really change how a bearing sounds, right? So as I said earlier, a pump could be in this building or it could be in a pharmaceutical factory on the production line. We can tell you that it has misalignment, bearing wear, electrical faults. All of them are similar across all the different pumps we have. And to your second question, it depends which customer, right? For the facilities, they couldn't care less, right? Some of them have some sensitive, what they would call IP, so the temperature the machine is running at, the RPMs, the way the process, and we alleviate those concerns. They're typically not an issue. When we talk to OEMs, it gets a bit murkier, right? And at the end of the day, they can either join us or do it themselves. And we know from some that tried that they can't do it themselves.
Hey, so one thing that I was wondering about is the sort of up to the cloud, the like first mile stuff that you have to deal with at your node, which you can power and have on like Ethernet or Wi-Fi or whatever. It could be secret, but like, did you roll that yourself, or did you build on some platform?
Mm-hmm. So, up to the back end, the question was how much of the full stack did we build ourselves, specifically the connectivity.
To get all this stuff up to the
cloud. We built everything ourselves, up to using open source technologies for backend and databases or whatnot. For two reasons. One, 6 years ago, nothing existed.
Oh, right, yeah.
Unfortunately, I wish we started now. Life would be much easier. And by controlling the full stack, it gives you much better control for edge computing, much better control for different environments. You can use cellular, you could use Wi-Fi. It gives us real flexibility, basically. So we did all of that in-house.
Hey, you talked about how you wanted to expand it to more companies because it was like 12% of companies had that. So at this point, with wherever your price point is now, how many of these sort of companies, or the 88% or whatever, can you actually reach? And when would you be able to?
Reach is a good question. How many do we sell direct to? Fortune 500. So not a lot, right? You have 500 companies by definition, right? Each has 50, 60 facilities maybe or whatnot. But through our channel partners, we managed to get to 5,000 facilities, right? So it's not continuous. It's more Auguscope, more portable tool, a HVAC technician going on site, recording, knowing what the health is, going to the owner saying, look, I need to replace a bearing or whatever. But you already reach 5,000 facilities. there are estimated 5 million commercial facilities in the US. So not enough.
Do you think that as you keep doing this, the price point comes down enough that it starts to reach those?
Yeah, so the question is, as the price point comes down, can we reach more? We started in the industrial side because that's where the problem is large enough to support the current price point, and our price point comes from the cost of technology, right? We're using MEMS-based sensors, which just recently, just this year, got to a point where a MEMS sensor is as good as a piezoelectric sensor, which is the old way of doing things. And the biggest difference between the two is that MEMS sensors obey Moore's law, and piezo don't, right? So next year, it will be half the price. Year after that, half the price. And we could go into rooftop units, we could go into smaller machines. So the goal, yeah, ideally we were everywhere, up to your washing machine.
Hi, thanks for being here. My question is, you mentioned that if you have the machines being measured and the year goes well, you might want to throw away a whole lot of data. How are you deciding, or how are your customers deciding which data to keep and which data to throw away?
So today,
of the good data.
Yeah, so there's a hidden question of who owns the data, which is a really good question. So today, the customer owns the data. Every customer owns the data. And we have a perpetual, irrevocable, global license to use the data for our own needs, right? So we have the final say of what we want to keep or not. Today, we keep all the data because it's still small. The continuous platform, Halo, as we call it, was only launched in November, so only 4 months ago. So it's fairly small, and we're still in research phase, and we want to perfect the anomaly detection. So we keep all the data. But if we multiply this 5, 10x, we'll start needing to make changes in the way we approach it.
Hey, so you're saying that many motors have kind of the similar issues that they'll see, but do you capture sort of make and model sort of information, and how useful is that?
It's really useful. First of all,
how do you capture that?
So through the app, or through, we have direct access to our customers, and at the end of the day, it serves them better because they can issue a report with all of the details in it. We try to capture everything, so different machine attributes, like number of balls in the bearing, as an example, or number of vanes in the fan or the pump, help us do a better job. We can kind of estimate and guess them, but if you give it to us, we're better. Yeah. It also serves us in what we've seen earlier. When we go to the OEM, we can slice and dice the data based on make, model, number of bearings, number of ball bearings, or whatever.
Cool, thanks.
On one of your slides, you talked about a low energy vibration sensor. Is that a software sensor? Is that like a little ball switch or IMU that's wrapped? And is it used for anything other than wake up? Can you actually win information that's valuable for the ML from that sensor?
So yes, we use it. We sample every 5 seconds. We wake up the sensor to sample and store. It's actually a MEMS triaxial vibration sensor that is very low power and low quality. So the resolution is low, the noise level is high, but it's very low power, and it's enough for us to get a sense of what's happening.
The human vibration sensors always looks like a bit of a black art, which you might have joked about. I'm curious, given that you've built your network and actually have put examples out of, if you've actually done kind of cross-testing on how good humans are actually at doing that.
Well,
I know it probably differs by the thing they're looking for too.
So there's a lot of variance, you'd be surprised. What we can do over time, and it's like a whole class of different algorithms that Amazon uses or Netflix for recommendations, is we can say, this vibration analyst is good in bearing wear, but he's not good in the rest, in misalignment. This analyst is great in this, but not that, and we can give different weights to different people when we train the algorithm. So the answer is they're not cohesive or
I have one question regarding EMI, the effects of EMI. And you mentioned each of those wireless sensor nodes send data to the central node through Bluetooth. So I'm wondering, of course, the environment, those equipment, those machines running in the site will have a lot of EMI generated from those equipment. Yeah. And how those things will affect the communication QoS, and also I'm wondering, do you have any customer which has a lot of RF devices in the site, which could cause a big challenge for the communication?
Yeah, so the question was around electromagnetic interference on site in these facilities, as well as in the RF domain, right? So a machine itself, typically, and we've never encountered something different, so I'll say typically, but it's almost always, emits magnetic emission in a very low frequency. The frequency of the RPM, which is 60 hertz, right? It doesn't interfere with Bluetooth, which is 2.4 gigahertz. We have encountered facilities that said, I won't allow Bluetooth in my facility because it may interfere with my control systems. And we're kind of steering away from those segments. But nuclear power plants have that, and others. So if they don't want us there, we won't go, right? Even though we'll try very hard, and then finally, at the end of it, understand that we're not wanted. You could go to a wired solution, but we choose to focus on the segments where we have a better fit now, and in the future, maybe we'll go upstream to those critical facilities. Microphone?
So it's interesting. Kind of goes back to the case where he said like 95% of the day is fine. So I'm sure you probably have a hard time sometimes convincing people saying that there might be a problem, but we don't know what the problem is. We have to look at the data, but we have to obviously have to pay. I guess that goes to the business model, but it's not like, I guess, a ESCO or there's no slight savings, right? So how do you convince people that if we go in and we look at something, and you're probably telling them that there is probably something there, but we need to look and give us a chance?
Yeah, so it's a good question. This is what I mentioned earlier by being a vertical company, right? We're here to solve this problem. And we have an end-to-end solution. So we don't come to you and say, here's an anomaly detection algorithm, try it. If something comes up, call us. Or we don't know. We come in and we sell diagnostics as a service, right? So our business model is we give away the hardware for free, and we only charge an ongoing subscription per machine per year for the services of diagnostics, including the automated results and the expert verification when needed. So there is no such thing as us going to a customer and saying, look, something happened, but we don't really know what it is. We would prefer flying someone over there and paying the extra cost to make sure they get the best value and service they can.
So a lot of times you'll have to actually, you'll send someone
It didn't happen until now. But typically, again, we have the three layers are mostly an internal challenge of scale, right? So we separate into 3 steps just to make sure that we have one algorithm that is specifically designed to detect anomalies, right? When this happens, it goes straight to the other algorithm that detects what's wrong. When that's finished and there is some kind of confidence issue, only then it goes to the human expert. And we expect that because we have 95% accuracy, right? The number of recordings that actually need to get to the expert are not that high. So it's more of an internal scaling issue. If you could get 1,000 people to just go over data all day long, it's a viable solution if you can afford that.
Good.
Cool. Thank you very much, guys.
So thanks everybody for being here. I hope you've enjoyed it. I want to say our next IoT New York number 53 is actually going to be on edge computing, so quite apropos. It will be on April 9th, hosted by our friends at Datadog, which I think is in the New York Times building, if I'm not mistaken.
Yes, it is.